Welcome back to part 2 of implementing the bisection method in Python. And in the last video, we implemented the actual function, and we called it, but we did not evaluate it. So now what we're going to do here is we're going to say, we're going to print out our root, our estimated root. We're going to say estimated root. And then we're going to say print out function at root value. And what we're going to simply do here is take the function of our root. So we calculated our estimated root, and what we're going to do is we're going to say, we're going to call our function at that root value and see if it actually equals 0 or not. So we're going to run this. So here we have it. Our estimated root is negative 1.99999, and as we can see here, that's basically 2. And our estimated root value is approximately 0, almost, to the negative 9th power. So, and we can see if we changed our tolerance, our error is going to grow. So we can see here, now our root value is almost 0. Not necessarily the best. But if we grow this to, let's say, 15, we have a maximum iteration reached. So we need more iterations for the bisection method. So let's make this 300 iterations. But before we do that, we're going to say print out iterations needed. So we're going to print out our iterations. And so if you wanted to get value basically within machine precision, for tolerance, you would need approximately 51 iterations of the bisection method. And so now what I'm going to do is I'm going to add some fancy printout statements to simply give us an idea of what's going on underneath the scenes. So we're going to say A. We're going to print out our A value. We're going to print out our M value. And we're going to print out our B value. And we're going to print out a nice little line. And we're simply going to print out the string of A, string of M, and string of B. So now let's go to the 7th power. So here we have it. We have A, B, and M, and it shows our division. So we can see here that our M value is between our M is calculated as A plus B divided by 2, and we adjust B as such, so B is now equal to M. And we simply grow these two values. As you can see here, our A and our B are going to become extremely close. And so the stopping condition is simply B minus A. And now is that value less than 1e to the negative 7th? And so what exactly does 1e to the negative 7th even mean? So we're going to print out tolerance, say plus string of 1e to the negative 7th. Alright, that's not what I wanted it to do. Let's say 4. Basically, what it is it's 1 times 10 to the negative 7. So here it is, 1 times 10 to the negative 4 is this value. So you simply say this B minus A, if that is less than 1 times 10 to the negative 7, then we break. So that is the stopping condition for this. Alright, and now what we're going to do is we're going to implement a sufficient number of iterations in our function. So as we stated before, here is the equation without proof for the sufficient number of iterations, n. It's given by the natural log of v minus a. So what we're going to do here is we're going to say import math. And what we're going to do is we're going to say, instead of having a max iter that is going to be passed in, we're going to say max iter is now going to be math.log2 of b minus a minus math.log2 of our tolerance. Oops, everything lagged there for a second. And divided by math.log2 of 2. So now we're going to say print out max iterations, max iter. So there we have our tolerance, and so we're going to run this. So bisection takes 4. We need to adjust this, get rid of 300. Unsupported operands here. So foolishly I put brackets around this, which made this a list. I want to put parentheses. So can only concatenate string, not float to, let's see. Okay, there we go. That's an easy fix. So there we have it. Our maximum iterations is 24.8. So what we can see here is we fed our bisection method a tolerance of 1 e to the negative 7th, and we can see here that our root is only off by 1 times 10 to the negative 7th. So now let's change this to 9. You can see here that we actually did better than expected, and we needed only 32 iterations. And so now we can say 15. We needed approximately 51.4 iterations. And so this is a very cool way to fix our improve our bisection method. That way we don't have to always feed in maximum iterations. We can simply just calculate it on the fly. And what we could also do is we could say if our maximum iterations is, let's say, bigger than 1,000, we could simply break. Simply because if our bisection method is taking that long to find a value, then there's obviously a problem. Not necessarily with the program, but with our choice of method. Because later on, we're going to introduce Newton-Raphson method, which is an extremely fast method, and it is simply an improvement on the bisection method. However, an improvement in terms of performance, not necessarily procedure. So thank you for watching this video, and hopefully you guys have learned about the bisection method and how to implement it in Python. So stay tuned for future videos.